do the, oh, yes. But since I just want you attempting it for tomorrow, I don't think it's fully due tomorrow. I'll show you what that looks like. Thank you, though. Thank you, thank you, thank you. Okay, parametric equations. Do you guys like how the screen is bigger this year? But it's like hanging off the top, so then it's kind of awkward. Oh well, best we can do without adjusting and. Okay, parameter. Who's t? Time. Okay, so t for time. I mean, that's the most basic application of parametric equations. T for time. Last year, when we talked about motion, and we talked about things going up and things going down, technically it was two-dimensional motion, what we call rectilinear motion. Why? Why could we only do two-dimensional motion last year? Only two variables. And one of them needed to be time. Y of t, x of t. I mean, sometimes I guess we talked about y equals f of x, but really we weren't really doing much calculus with it, which is why the position function was either s or x. We didn't talk about y equals f of x with motion, at least not really. And so when I talked about like things dropping off cliffs or things like going up and going down or shots being fired, I would try to visualize it or help you guys visualize with like the normal motion, like throwing a ball that you're used to, but technically we never did this last year. Because this would require horizontal change, displacement, vertical change, displacement, based on time, 3 variables. So we just did straight up, straight down, straight right, straight left. We never put the two together. We never did up, down, and right, left. It was either just a right-left model or just an up-down level. That's all we could handle. Until we introduce the parameter t. Now the ironic thing is we totally did t last year, but we didn't do x of t and y of t. Calculators on, mode, hit, par, selected. Not function, par. Calculators on, mode, par. What happens when you go to parametric mode in your calculator and then go to y equals? Some of you already did this. Some of you are doing it now. What do you see for each set of equations? What if I was to go ahead and say x of t is equal to, I don't know, 5t minus 1. Hey, you hit the x button. It's now a t, 55t. Oh dear. 5t minus 1. It's no longer an x function, it's a t par, then it's a theta pole, then it's an n sequence mode. Interesting. What happens if you hit graph? What went wrong? We need a y. Parametric equations, something that's defined parametrically is defined in terms of t, but both x and y are defined in terms of t. So if I was to make it something like t squared, then all of a sudden, life is a bit more exciting. So in parametric equations come in pairs. X is defined in terms of t, y is defined in terms of t. So at a certain time, horizontally what's happened and vertically what's happened as far as how much it's moved. So then coming back here, first of all, parametric equations are useful just in dealing with three-dimensional motion. And what's our world? A three-dimensional world. So if we're trying to actually pattern true motion, true movement, we need to be able to go beyond what we did last year. So to model the when and not just the where. So we could talk about y equals f of x like a parabola. We could be like, hey, this is the path, but we couldn't actually talk about when a certain object is at a certain location or whether it's going forwards or whether it's going backwards on that path. We could talk about the where without the parameter. We could talk about the when, but only in two-dimensional. But now we can talk about the when in three-dimensional. No, sorry, I just said that backwards. Last year we could talk about the when in one-dimensional motion, right, left, up, down. Now we can talk about two-dimensional motion and how much of a jump to go to three-dimensional. Lo siento. But it is a chapter in pre-cal that we skipped because we weren't going to physics specifically. But anyway, if you're ever curious about three-dimensional vectors, chapter 11, the pre-cal book, you can borrow it anytime. Okay. So we have x of t, and we have y of t, and somehow we have to relate everything together. Just super quick vocab. The resulting path is called a plane curve, but I'm just going to call the path. You don't really need to know the plane curve for AP stuff, etc., etc. Okay, all background stuff, right? Let's talk about some more details. Ooh, that's not going to work well. Parametric equations. If you're dealing with a certain time interval, you're going to have an initial point, you're going to have a terminal point. If you have a time interval, so for a set, t is within, let's use some interval notation, a to b. Your initial point would be x of a, y of a. Your terminal point, just order pairs, that's all I'm doing. X of b, y of b. Besides those quick little units in pre-cal that you guys covered, your entire mathematical career graphing has been in function mode, basically. Your mathematical career, besides those two little, or actually one little chapter in pre-cal, you've been in function mode. So, if I ask you what y equals x squared looks like, if I ask you what approximately y equals 4e to the 5x looks like, if I ask you what y equals 7 over x squared minus 1 looks like, you might have different familiarity with each of those functions, but you have an idea based on the basic graphs forever card number 1. But parametric, without eliminating the parameter, ooh, help, that was summer packet, without eliminating the parameter, what did we do when we eliminated the parameter in the packet? Solved. Substituted for t. Yeah, you could say that. We solved the x equation for t is what I would have added to that. Solved the x equation for t and then plugged in for t, aka eliminating t. So without eliminating the parameter, which means, hey, let's go back to just what the path looks like. I don't really care about the timing. Without going back to function mode, we're not really sure what these all look like. So it's going to be very helpful to make tables based on t, values of t, finding quantities of x and y. So what's our new independent table? T. And now who are dependent? Both x and y. So in order to find x and y, we're going to have to plug in to find them. T, well, we're going to have to look at the range. And if they gave us something like an a to a b, then we could say, all right, let's start at t equals -2. Let's stop when t is 10, and let's think about all the different possible values we should probably put in between, and then plug and chug. Why do you think number 2 is important in the sense that we should always, 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 which we've done even in algebra, but always, always, always plug in with t increasing? Why is that important? You have to graph it like that. And why would you have to graph it with, I mean, with like x, y tables, couldn't you theoretically have put the points in any whatever order you wanted as long as you got them on there? Because with parametric, t is time, and time only goes one way as far as modeling. Does that make sense? So we have to go from the lower values of t to the higher values of t because time, for our purposes, is always going forward. If you want to go study more about time, this is not the class. But there's a lot out there, and your mind will be boggled. Or it'll look like nonsense, or both. So we always want to go in increasing values of t, hence why I'm starting at that. I mean, and that's what we do for x's too. Like, it's not that different, but it's super important that we look at the direction, because direction is important. The orientation is going to be the direction of movement. So when you're putting the points, sometimes we'll be putting the points, like for our little parabola, putting the points from left to right, but maybe we'll be putting the points from right to left. And you put little orientation arrows in order to show what direction the movement is. Calculator, I think we already talked about, we kind of did a preemptive. We went to the par mode. We're going to play around in there. Your window. Did we talk about it? No. Your window. There's going to be something new, or at least new for us in calculus. There's going to be a T-min and a T-max and a T-step. The T-min, T-max, T-step, in order to think about what these should be, you can try to do Zoom standard, and it'll kind of reset it to whatever your settings are. But the T-min, T-max, T-step is going to depend on degrees versus radians. Degrees, you're going to have usually big intervals for T. Radians, you're going to have smaller intervals for T. Degrees, radians. But I'll also say your interval. Because regardless of degrees, radians, if your interval is like -2 to 3, that's what you should make your T-min, T-max. Because if you hit like the little Zoom standard, it'll probably change your T's based on degrees. But here's something else really weird. Parametric equations do not have to just be using T. They could also use theta, like x of theta, y of theta. I haven't really seen any other variables in use as far as with our information or what we're covering. But parametric basically just means a third variable. T is the most common, but there can be a theta also. But our calculator is not going to use theta for parametric. It's always going to use T. So sometimes we'll have to kind of be like, oh, it says theta? That's weird. All right, whatever. T is what I'm going to think of it at. And the quick note for graphing. Ooh, you guys see some new words? A graph can draw. Why can't I think of how to say this word in my mind right now? Parametrized? Parametrized? Anybody want to ask Siri how to say it? Curve only over a closed interval, so that the portion it draws has endpoints even when the curve being graphed does not. Here's the warning. If you have a closed interval, there is a beginning to that motion and an end to that motion. Your calculator, depending on the window, will not know the beginning and end unless you tell it what it is. So it might show more of the path than it should. That's the long story short of the graphing. All right. So what if you have the graph? Oh, do you guys need me to go back? Can I double page it? How is it? But there's no, right? Like there's no ter. Parameterized. Isn't that weird? I would have never guessed terized. Terized. Huh. Thank you. No. No. It's more of just a heads up. Okay, so describe the graph of the relation determined by. I want you guys to see if you can get your calculator to give what it needs to give. Oh, did I just show the window? That's lame. That's okay. Not a big deal. We're running short on time anyway. If you were to throw in this x1 equals t, y1 equals 1 minus t squared, use the parametric mode to draw it. Why would you have only gotten a partial downwards parabola? Why would you have gotten a parabola at all? Yeah, you see the squared, and the squared's in the y, right? And so if you were to, how do you by hand think of any of this? You eliminate the parameter. So that would have been, well, t is already equal to x, x is equal to t. That's super easy. So we're really just dealing with y equals 1 minus x squared. That's the path. So if we were just doing function mode, and if we were just eliminating the parameter, ignoring t altogether, we'd say, oh, no big deal. It's a parabola shifted up 1, going down. But why did the graphing calculator only show it half? It had time starting at 0. That's pretty natural, right? It's a good assumption. Time starts at 0 for a model. When would time start at a negative number? Yeah, if it was like in reference to. So like, oh, at 9 a.m. here on, oh, what was going on at 8 or at 7 if the thing was already in motion? So it could be that you have some sort of reference point that you go before or after. So this is what our graph made initial. So the beginning of the movement, if you plugged in, which you could have done just plugging in yourself. If t is 0, x is 0, and y is 1. So you know that starting at the top of the motion, the orientation is going to be going down. But do you guys see what I mean by it kind of follows degrees radians? Because Zoom standard said 6.28. That's 2 pi. It's a lot like Zoom trig in the sense of how it naturally just sets the t. But there was nothing technically in this problem that said what to make our time. So I guess you could have technically had time going negative. There was nothing restricting it. But the calculator naturally, Zoom standard, would have started at 0, which is pretty natural for it to do. Yeah, Aryan. The graph wouldn't have moved. You would have seen more of it, so there would have been an earlier starting point on the parabola. Does that make sense? So it's not so much of a shifting of the graph as a shifting of the starting point on the parabola. Are we good? I think we're good to graph it and draw it too. But if you weren't in radian mode and if you were in degree mode, Zoom standard would have given you 0 to 360 with a t-step of 5 probably, somewhere around there, 4 point something, 5 point something. So that way you at least know kind of where the window's coming from. It's coming from degrees or radians. Unless they give you an interval, then you set it to be what you need it to be. Okay. Nice thing is, Summer Packet totally already walked you through this. Oh my goodness, this is way too easy. We just did this one. All right, let me get you a harder example. Let me freeze the screen so you can at least introduce or start the eliminate the parameter. But let's get you a much more fun one. How about this one? Which, to be honest, in most books, this example I'm going to give you would not show a t. It would probably show a theta. But in calculus, it's going to show a t instead. That's more fun. Okay, so when we eliminate the parameter, we're looking for the path, ignoring the time. We can't just ignore it and say it's not there. So we do what you guys said. Get the t by itself, plug in. Get the t by itself in the x equation, plug into the y equation. But why did this example just get funky? Yeah. Why is this example harder than the other one? Yeah, there's trig. What are we supposed to be getting? Yeah. How do you get t? Divide by 3 and cosine inverse. And then plug in a cosine inverse. To him? What's 3 sine times cosine inverse of x over 3? Or, are we down to the example part? I have it on this page. Or, we say, psh, that's easy, it's just a circle. What? Why is it a circle? It's the same example. It's the same example. So if you're still writing it, it's still up there. Why is it a circle? It's trig. What really cool trig equation, trig identity do we have? What's the easiest trig identity? We talked about it yesterday. Pythagorean. What is the Pythagorean property? Sine squared plus cosine squared is 1. You remember this from last year. Wouldn't it be super cool if I could just get rid of the t by using some nifty trig property? Couldn't I say that cosine is x over 3? And couldn't I say that sine is y over 3? T's gone! How is he gone? Because I could solve for cosine, solve for sine, and I could relate the two together. That's the point, is we're trying to get the x's and y's together. Well, sweet, sine squared plus cosine squared is 1. Guess what? This is just a circle with a radius of 3. Dun, 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 dun. This is what pre-cal, you did in pre-cal, second semester, 2 years ago. We haven't done any derivatives yet. That's not going to happen until the end of the year. Well, no, we'll do parametric derivatives earlier. How'd I forget that? I didn't go over any questions either, did I? All right, beginning of tomorrow, I'm going to collect the packets and see if you guys need any clarification. I got distracted. Struggle. But I want you guys to try section 1.4 homework as much as you can for tomorrow. Sound good? All right. See ya. Happy Thursday, almost Friday, almost weekend.